Hello and welcome to the Explainer. We're about to uncover the secret behind this little device right here, the hard drive. It literally stores our entire digital lives using a force you can't even see, magnetism. And today, we're going to figure out exactly how it does it. Okay, so let's just dive right in with the big mystery. Take a look at this thing. It's an absolute marvel of engineering that holds, gigabytes and gigabytes of data using just magnetism. But how? Really, how can this invisible force be controlled so precisely that it can write and read the ones and zeros that make up, well, everything you do on a computer? That's the core question we are going to solve together today. So, to crack that hard drive code, we've got to go back to basics. Before we can even think about using magnets, we first have to understand the fundamental rules that all magnets have to play by. Now, this is rule number 1. And you've probably felt this yourself, right? You bring a North Pole to a South Pole, and they just snap together. But then you try to force two North Poles to touch, and you can actually feel that invisible cushion pushing them apart. That simple push and pull is what governs every single magnetic interaction. But how do you see an invisible force? Well, this is how. If you sprinkle tiny iron filings around a magnet, they physically trace out its field of force. And notice how they don't just stick evenly all over it. No, they cluster right at the ends. This shows us visually that the magnet's power is really concentrated at these 2 points, what we call the North and South poles. So you might be thinking, okay, easy. If I bring an object near my magnet and it sticks, I've found another magnet. But hold on, it's not quite that simple. A magnet will absolutely attract another magnet, for sure. But it'll also attract a plain old iron paperclip, which isn't a magnet at all. So you see, attraction can be a little misleading. And this brings us to a really crucial question. If attraction isn't the final proof, what is? How could you come up with a foolproof test to tell the difference between a true magnet and just a piece of magnetic metal like iron? Just think about that for a second. And here it is. The one true test for magnetism is repulsion. Let's just walk through the logic here. If one end of your magnet attracts the object, you flip your magnet around. If the other end also attracts it, well, then your object is just a magnetic material. But if that other end repels it, if it actively pushes the object away, then you can be absolutely certain you've got two magnets, because repulsion only, and I mean only, ever happens between two like poles. All right, so we figured out the rules on the outside. Now let's zoom in, way, way in, to understand what's actually happening on the inside of a material that gives it these incredible powers. The secret, it turns out, is something called magnetic domains. The easiest way to think about this is that every single atom is like a teeny tiny little magnet. And in magnetic materials, these atomic magnets like to team up in these little neighborhoods we call domains. And you can see the difference so clearly right here. Look at the image on the left. In a normal piece of iron, all those little domains are a jumbled mess, pointing in every which way. It's like a disorganized crowd. All their little forces just cancel each other out. But on the right, in a magnet, look at that. The domains are all aligned, like soldiers in perfect formation. Now all their tiny forces add up to create one large, powerful magnetic field. This whole domain idea also explains something that's, well, kind of weird. If you take a bar magnet and you snap it in half, you don't get one north piece and one south piece. Nope, you get two brand new, smaller magnets, each with its own north and south pole. And that's because you're just splitting that line of soldiers. Each new piece still has its own perfectly aligned formation of domains inside. So, applying what we've just learned, thinking about those domains, can you see why it's totally impossible to have a magnet with only a north pole or only a south pole? The answer is right there in the structure. Every single domain has two poles, so any collection of them, no matter how small, is going to have two poles as well. Okay, this leads to a really powerful idea. If magnetism is just about lining up these domains, well, that means we should be able to control it. Can we actually force those domains to line up on command? And maybe even scramble them up again? Well, the answer is a big yes. So we can induce magnetism in a couple of ways. The old school stroking method. It's kind of like combing messy hair. Each pass with a strong magnet pulls more and more of those domains into alignment. But a much more powerful way is to use electricity. If you place the material inside a coil of wire and run a current through it, you create a really strong magnetic field that basically snaps all the domains into line all at once. Now here's a key point. Not all materials behave the same way. We basically put them into two groups. We've got soft magnetic materials, like pure iron. They're easy to magnetize. Their domains line up without much of a fuss, but they also lose that magnetism just as easily. Then you have hard magnetic materials, like steel. They are tough to magnetize, but once you get their domains lined up, they tend to stay that way for a long, long time. And this table just lays it all out perfectly. Soft iron is great for temporary magnets, like the ones we're about to see. And steel, well, because it's hard to magnetize but also hard to demagnetize, it's perfect for making permanent magnets. And would you look at that last point? Recording media and hard disks. The mystery is starting to come together, isn't it? You see, it's all about choosing the right material for the job. A junkyard crane needs a magnet that it can turn on and off. So what do? You use a soft iron core, wrap it in a coil, and run a current. The magnet turns on, bam, it lifts the car. You cut the current, the domains scramble, and the magnet turns off, dropping the car. You couldn't use a permanent steel magnet, right? You'd never be able to let go. So we've talked a lot about this magnetic force and these aligned domains. But what does the actual field of force created by those domains look like in the space around the magnet? Well, guess what? We've already seen the answer. Those iron filings aren't just a cool party trick. They're physically lining themselves up along the magnet's invisible field of force. They give us a perfect map of its shape and its direction. You can literally see the lines looping out from one pole and right back into the other. Now, to make this easier to study, scientists draw these patterns as diagrams with what they call magnetic field lines. There are just two simple rules you gotta remember. First, by convention, the arrows on the lines always point out of the North Pole and into the South Pole. And second, the closer together the lines are, the stronger the magnetic field is in that spot. See how they're all crowded and bunched up right at the poles? That's where it's strongest. Okay, let's take a quick step back for a second. We started this whole journey with one simple question. How does a hard drive use magnetism to store all our information? And to answer that, we've actually covered a ton of ground. So let's finally put it all together. The spinning disk in a hard drive is coated with a hard magnetic material, like steel, perfect for storing information permanently. The little reed/write head that flies just above it has a tiny electromagnet made from a soft magnetic material, like iron, which we can turn on and off in an instant. To write data, this electromagnet flips the magnetic domains in tiny, tiny spots on the disk, pointing one way for a 1 and the other way for a 0. And that's the secret. You use a controllable, temporary magnet to write a permanent magnetic code. So we've just seen how we control these tiny little magnets to shape our entire digital world. But this leaves us with one final and kind of massive thought. What about the giant magnet we're all living on right now? What does Earth's own massive magnetic field do for us every single day? Well, that's a story for another time. Thanks for watching The Explainer.